Day 2. Continuing on with conics, we have ellipses. So, an ellipse. It's a shape formed when a cone intersects a plane, like this, at an angle to the base. So, not all the way down to the base. It's a closed curve that looks like a stretched circle. That's what an ellipse is. So, some ellipses in the real world, I didn't go over this with circles, but I mean, we're more familiar with circles. We can see ellipses in multiple places. Astronomy, it's used in astronomy. There's several. I only put 2 on here. The orbits of planets and comets around the sun are elliptical. Acoustics, this is really interesting. I have a video that if you were in class, I would play it. But in concert halls and auditorium, elliptical designs can enhance sound projections. Sound waves emanating from a source of an ellipse can reflect off the walls and converge in a fixed location, enhancing the auditory experience. I'm not going to play that video on this video. But some key components to an ellipse. Since it's not a circle, we don't have a radius because it's not equal around the entire thing. But we do have a center, and that center is going to be the same as it was in a circle. It's going to be our H and K that we see in our formula. But we can have an ellipse that looks like this, where H and K is the center of that. We have a major axis and a minor axis. The major axis is the longest diameter. So that would be this piece right here. That's called our major axis. We denote that with the letter 2a, we denote that as 2a, where a is the distance from the center to one of the vertexes along the major axis. So that, or we can do the other side as well, but just from the center to one of the vertices, that's what we would call a. 2a would be the whole thing. The minor axis is the shortest diameter of the ellipse, so the diameter right here, and then we would denote 2b, where b is the distance from the center to the vertex along the minor axis, so just one of those sides like that. So we need to understand what a and b are because they appear in this formula. So this is similar to a circle, except a couple differences is we don't have a radius, so an ellipse will always be equal to 1, and then we have these denominators that we can have as well. So what are those? Here's this is a horizontal ellipse, and this is what the equation looks like for that. So we have x minus h squared over a squared, and then b, and remember a has to do with the major axis, and then b has to do with the minor axis, and that's also equal to 1. We can also have a vertical one where if we look at our denominators, if our denominator is bigger under the y, that would mean that our ellipse is vertical. Our major axis is longer than our minor axis, type of thing. So with horizontal, your major axis will be bigger, longer, going horizontally, which is why it's bigger, and that has to do with a, which is what we talked about a second ago. Remember, 2a is the diameter, a is half of that, b is the diameter of the minor axis, 2b, sorry, and then b would be half of that. So in both cases, h and k is the coordinates of the center. A would be half the length of the major axis, so one of those, and b is half the length of the minor axis. So we're going to practice graphing some of these. Even though you don't have to graph these by hand on a test, I think it helps in terms of A and B, rather than having to memorize some formulas to figure out those, especially with what we talk about next time. But let's just look at how to relate a graph of an ellipse to an equation. So our H and K, we can look at that graph and hopefully see that our center is at 3, 1. If I know what that center is, and I know that this is horizontal, I can draw a line from the center to the edge of this ellipse and figure out what my A is, because that's the length of that. I go 1, 2, 3, 4. So my A is 4 here. And my B is going from the center to the other vertices, the shorter one, and I count up 2. So if this is my equation for a horizontal ellipse and I know what h, k, a, and b are, now we can plug those in and figure out what the equation is. I'm plugging those in as a squared and b squared, and then I'm going to simplify just to show you this is what that equation would look like. Okay, same thing here. This is just a vertical one. We can see our center is right there. My major axis, count up to the edge of that, which would be 7. And my minor axis would be 3, or half of 3. My b value would be 3. And so that's my a and my b. Since this is a vertical one, we're going to be bigger with a. So, or the y is bigger, the denominator of y is bigger. If I substitute all this in and kind of simplify, x minus 0 is just x, and then I square the denominators, and I get the following. Okay, let's look at an example where we're determining if this is vertical or horizontal, and then finding the center and length of the major and minor axis. So looking at this, I'm going to start with my center, and that's just h and k. So my center is 5, 2. It's horizontal. It's horizontal because we're bigger with x. Like 25 is bigger than 16. So we're bigger than x. So our major axis is going to be bigger going horizontally. So I'm bigger with x, and then I look at my h and k. It's 5, 2. I can see that from looking at the equation. I'm going to go ahead and plot that on here, and then I'm going to use this to find a and b. So actually, I'm not going to use this to find a and b. I'm going to find a from here. So if I know a squared is 25 and b squared is 16, then I know that a is the square root. A squared is 25, then a is the square root of 25, which is 5. And the same with b. And so now I can count over from that center 5 in both directions, left and right, and then up and down in both directions 4. And now I can see what my major axis length is. I just go all the way across, it's 10, or you can do 2 times A and 2 times B. And either way, we should get something like this. Determine whether the ellipse is vertical, horizontal, and find the center and length of the major and minor axes. This is like one we had yesterday where we had to complete the square. And we do have an A value that needs to be factored out here. So I'm going to start by grouping X and Y's and then complete the square for both groups. So the first group, that's that. The second group, I'm kind of going ahead. I have 9y squared and negative 90y. If I divide a 9 out to factor out that a, I'm left with the following. I need to move my 225 to the other side. And I'm going to start with my x's. 6 divided by 2 is 3, and I square that and I get 9. So I'm going to add 9 over here. If I do negative 10 divided by 2, that's negative 5. If I square that, that's 25. But I'm not, remember, this I factored out that 9. This is really 9 times 25 that I'm adding to the other side. So that's 225. Those 225s are going to cancel because one's negative and one's positive. This x squared plus 6x plus 9 would factor as x plus 3 times x plus 3, which is x plus 3 squared. We're going to leave the 9 out here in front. And then y minus 5 times y minus 5 is y minus 5 squared. That all equals 9. Now, ellipses and hyperbolas all have to equal 1. So we don't have 1 equaling 1. So we're always going to, if we have something other than 1, we're going to divide both of these fractions and simplify by, we're going to divide them by that number so we get that equal to 1. So if I look at the x's, I'm still going to have 9 in the denominator. The y's, the 9s are going to cancel out, and I end up with just that. I can leave this as 1 if I want to, just so I can have it consistent. I can figure out what A and B are. But this is horizontal because I'm bigger with X again. My center is negative 3, positive 5. So I'm going to go ahead and plot that. And then I'm going to figure out what A and B are. So 9 is A squared and 1 is B squared. If I take the square root of both of those, I get A equals 3 and B equals 1. So once I find that, and I'm sketching this out to get a visual, I can count that diameter, and that's the major axis has a length of 6. And then the minor axis, B is 1. So if I go up 1 and down 1, then I have a length of 2. A minor axis of length of 2. And I get something like that. All right, let's write the equation of ellipse given it's vertical. So I'm told that it's vertical. I'm told the center. I'm told the major axis length is 10 and the minor axis length is 4. So let's go ahead and start here. I'm going to start by graphing this. So I have negative 2, 0. I'm told that it's vertical, so the major axis is has a length of 10, which means I need to go up from there 5 and down 5. That whole length needs to be 10, with the center in the middle, obviously. And then the minor axis, I'm going to go over 2 and to the left and over 2 to the right. And there we can see what is half of that is. So A is half the length of the major axis, B is half the length of the minor axis. So I went up 5, so that's A. I went to the right or left 2, so that's B. And from there, I can plug in whatever I need to. So if I know A is 5, then A squared is 25. If B is 2, then B squared is 4. And so I just put those under, and I'm bigger with Y. We have to remember that I'm bigger with Y. I even have that note for myself. So I'm bigger with Y. So that 25 needs to go over or under Y, and the 4 needs to go under the X. All right, guys. So y'all have some practice over this, worksheet 13.2. And then after that, you need to complete the following. These sections should have already been done. What you're doing next that's added onto this is the ones after that, the ones that have to do with an ellipse.